All right, hi everybody. Let's get started. I hope you all had a restful weekend with no chem or bio exam to study for. We have our next Achieve homework. As you all know, it'll be due next Monday at 9 a.m. And I'll post that later today or tomorrow. The McLean lecture, I don't know if you've heard, but Chemistry Club is hosting a professor from the University of Michigan. He's a professor in the School of Pharmacy. And so there's a flyer. I'll post this on Blackboard as well, but this is on Friday at 6:30 p.m. So he's going to give a lecture. I believe he'll talk a little bit about his career path to working in pharmacy, working at the University of Michigan. It'll be in some ways related to chemistry as well. There's an abstract here. I'll post this on Blackboard. I won't read it right now. But it is Friday at 6:30 p.m. in this room. If you're interested in coming, I encourage you all to attend. You do have to be here before 6:30. So there will be two professors guarding the two doors. They'll be open until 6:30 p.m. and then they're closed. And they won't be letting any other students in because we'll have the lecturer here and we don't want to interrupt the talk. So if you do just plan to get here a few minutes early so you can come in, find your seat, and we'll get it started at 6:30. So I encourage you all to be there. I will be there. Other announcements. So throughout the semester in our class and in your other classes, it's always a good idea to make sure the grades that are in gradebook is accurate based on the grades that you've earned. So we are human. Sometimes mistakes are made. We have over 90 students in Chem 1070, so there's a chance that some of the grades or a grade that's added to the grade book might be incorrect. So just double check for your own grades. Right now, the iClicker grades up until last Wednesday, I believe, are posted. So you can go, don't do it right now, we're about to start class, but after class, you can go into the iClicker website, check the grade book on iClicker, and just make sure that what's in the Blackboard grade book is accurate. 99% of the time it's accurate, but if there is a mistake, we want to make sure that is caught ahead of time. So that'll be true. We don't have the Achieve homeworks in gradebook yet, in the Blackboard gradebook yet, but those will be posted soon, so you'll double check those. And then anytime you get an exam back, it's always a good idea to check that your grades are accurate compared to a key, if the professor gives you all a key, that the professor added up all of the scores correctly, so you want to double check that. And then also to look through your exam to see which questions you got wrong. Think about why they're wrong. Think about what would have been useful to know or study ahead of time to get the answer correctly. So just keep that in mind for your future classes. I don't have your exams today, so it probably won't be until Friday. But keep that in mind as you go through your classes. Any questions about any of this information? Okay, so we are almost done with part one. We were just finishing up this table. So let's finish up the table. You all had time to work on it, so I'll just go through the last few rows. So we did iron 3-phosphate. The next one is iron chloride. We have 3 chlorine atoms. We have a metal. So we have an ionic compound. We have 3 chlorine atoms. Remember, chlorine has a -1 charge when it's in ionic compounds. If we have 3 of them, that's -3 over 1. So the iron must be a +3 charge. So we have iron 3 chloride. Remember, we don't use prefixes, so we don't say trichloride here because this is an ionic compound. We would use tri if it were a molecular compound. Next, we have a hydrate molecule. We have tin. Sn is element tin. Tin is an element that has a variable charge. We have 2 chlorine atoms, -2 overall. We only have 1 tin atom, so that must be tin 2. Actually, I need to write this smaller. We have tin 2 chloride. And then we have 2 water molecules, so that's dihydrate. We use the hydrate when we have waters, and then di signifies that there are 2 waters. And this is another ionic compound. Tin is a metal. It is to the right of the periodic table, but it's still left of the metalloids, so we consider that a metal. So we have an ionic compound. Sulfur dioxide, we have 1 sulfur atom, 2 oxygen atoms, so SO2. Both are nonmetals, so this is a molecular compound held together by covalent bonds. And then lastly, we have sodium, 3 sodium atoms, a phosphorus atom, and 4 oxygen atoms. We know sodium is a metal. It's on the left side of the periodic table. And then when you see multiple atoms like this, that's a good cue that this is a polyatomic ion, because otherwise we wouldn't know how to name this molecule. There's 3 atoms here. So this is the polyatomic ion phosphate. So we have sodium phosphate. We don't need any prefixes in here. Phosphate has a -3 charge. Sodium has a +1. That's why we have 3 sodiums here. So we have sodium phosphate. Sodium's a metal, so we have another ionic compound. Any questions about these naming rules, patterns, molecules? All right, that wraps up part 1. So we're going to move to part 2, which is all about the mole. Oh, there's this extra slide here. You may find this helpful in the future. It didn't really come up through our lectures, and a lot of this information is applied because you're given the name or given the formula. But if you're ever writing a formula and you don't know which atom to put first or last, atoms, except for hydrogen, that are more to the left of the periodic table appear first. So that's any cation. Any metal is going to appear first in a formula. And then if you have nonmetals, it's whatever nonmetal is more to the left of the periodic table that appears first. And then hydrogen is last, unless it's with an element from group 16 or 17. So here are 3 examples where hydrogen is last, if it's with lithium, nitrogen, or carbon. But if it's with water, sulfur, bromine, it appears first. And then if you have 2 elements from the same group, the element from the lower group appears first. So that was just an extra slide for you all to reference in case it comes up. And that's it for part 1. Now we'll go to part 2. So this is section 3.7 to 3.12. And in 3.7, we're just learning about what the mole is. So the mole is a unit conversion that we'll use, and it is a way to simplify counting atoms. So we refer to the number of atoms within a unit, a mole. For 1 mole of This is carbon. I want to start with carbon when I explain this. For 1 mole of carbon, the isotope carbon-12, that has the atomic mass unit of 12, there's 1 mole of carbon atoms in exactly 12 grams of carbon-12. 1 mole of atoms is 6.022142 times 10 to the 23rd atoms. This is the conversion that we use. We're going to use it in a lot of calculations. This number is called Avogadro's number. And it's abbreviated as capital N with a subscript capital A. So N for number, capital A for Avogadro. And we will not be using this many sig figs. We will use 6.022 for the most part, 6.022 times 10 to the 23rd atoms. Or atoms or molecules. We'll talk about that on the next slide. So I'll take that. So just like if you have a dozen bagels, that means you have 12 bagels. If you have a mole of bagels, you have 6.022 times 10 to the 23rd bagels. So it's a conversion to represent the amount of something that's present. So if we have a mole of carbon atoms, that's 6.022 times 10 to the 23rd carbon atoms. If we have a mole of calcium atoms, that's 6.022 times 10 to the 23rd calcium atoms. If we have a mole of molecules, we have 6.022 times 10 to the 23rd molecules. So 1 mole is 6.022 times 10 to the 23rd atoms or molecules, depends on what you're talking about. So using this mole as a unit limits our need to use really large numbers, because if we're talking about 1 gram of a substance, that can be, if it's hydrogen, that's 6.022 times 10 to the 23rd atoms of hydrogen. It's a lot of hydrogen atoms. So instead of using that large number, we can say we have 1 mole. And then we can use Avogadro's number as a conversion factor. So these are equal to each other. 1 mole is this amount of atoms. Same up there, they're the same values. So we can set that up as a conversion factor. In the first row up here, let's say we have the number of moles of a substance, but we want to know the number of atoms that are present. We can use this conversion. Or vice versa. If we know the number of atoms that are present, we can find the number of moles by using that conversion. So this is what this image says, or is trying to show here. If we start with moles of a substance, this is the top, we have moles, we multiply by Avogadro's number, and we get number of atoms. Or if we start with number of atoms, divide by Avogadro's number, and we end up with moles that are present. So let's say we have 0.300 moles of sodium. How many atoms are present? And then if we have 1.2 times 10 to the 23rd sodium atoms, how many moles is that? I'll give you all a minute to start working on this, and then I'll go through it together. It's not an iClicker question, but I did start the class on iClicker. So if you have a moment, now's a good time to join the class so you're ready for when we do have an iClicker question. Okay, let's do this first one together. So we are given the measurement of 0.300 moles of sodium. And we want to know how many atoms are present. So we're going from moles to atoms. We use Avogadro's number. We multiply by the number, 6.022 times 10 to the 23rd atoms are present in 1 mole. And so if we multiply 0.3 times Avogadro's number, we should get 1.807 times 10 to the 23rd atoms of sodium. Yes. It would be 3 sig figs. Thank you. So this is 4 sig figs. This is one extra. If we're rounding, we have 1.81 times 10 to the 23rd atoms. We have 3 sig figs because we start with 0.300 and that has 3 sig figs there. And then in the second question, we have 1.2 times 10 to the 23rd atoms of sodium. And to convert to moles, we want to cancel out atoms, so we use 1 mole on the top of the fraction and then Avogadro's number on the bottom. And this is 0.199 moles of sodium. If we're worrying about sig figs, we have 2 sig figs in the value given to us, so 0.20. Any questions on these? Yes.
Is there a reason for why it's 6.022? Is there a reason why it's that number?
Yes. I don't remember exactly how Avogadro determined this number. It might be that he was able to determine in 12 grams of carbon 12 there were this many atoms. That's probably in the book though. I'll see. I'll look it up. Good question. Other questions about this? Does anyone else know? You do? Tell me. What is it? I'm correct. Okay, so Avogadro determined how many carbon atoms were in a sample of pure carbon 12. And there were 6.022, 142, 10 to the 23rd atoms. Okay, other questions on this? We will use this conversion within larger conversions, converting between moles and atoms or moles and molecules. So if we have 1 mole of a chemical compound, that is 1 mole of its formula unit. So if we have methane, which is CH4, 1 mole of methane is 1 mole of CH4 molecules. If we have 1 mole of CH4 molecules, there's 1 carbon atom per molecule. So we also have 1 mole of carbon atoms. We have 4 hydrogen atoms per methane molecule. So if we have 1 mole of methane, we have 4 moles of hydrogen atoms. This is the same for all compounds. So if we have sodium chloride, if we have 1 mole of sodium chloride, well, we have 1 mole of the sodium cation per sodium chloride compound. We have 1 mole of the chlorine atom per sodium chloride compound. So we can use that conversion to determine how many of each specific atom is in some amount of the overall compound. Okay, this one's a clicker. You have 2 questions on your slide, and I think they're asking the same question. So you're going to get 2 iClicker questions, but the second one is not what's on your slide. It's a different question. But let's say we have 4 moles of carbon tetrachloride. Question is, how many moles of carbon are present? How many moles of chlorine are present? And then you have another question about carbon dioxide. All right, let's go through this. Make sure your answers are submitted. I'll give you 10 more seconds to get your answers in. Five seconds? All right. Okay, we have some mixed answers here. So if we have 4 moles of carbon tetrachloride, we can actually use a math equation. We have 4 moles of carbon tetrachloride. We want to find how many moles of carbon. Well, in 1 mole of carbon tetrachloride, we have 1 mole of carbon. So we have 4 moles of carbon in 4 moles of carbon tetrachloride. For chlorine, if we have 4 moles of CCl4, for chlorine, since it's CCl4, we have 4 moles of chlorine for every 1 mole of CCl4. So that means we have 16 moles of chlorine atoms for every 4 moles of carbon tetrachloride.
So we can put, all that compound in the parentheses with like 4, right? This is like the same thing, 5 by 4. Like for carbon and multiply, the chlorine. That's what I did. Like you say, you could write CCl4 in parentheses sulfur 4.
And then multiply. Yeah, you could do that. So if you did, and then say you have now 4 moles of carbon, 16 moles of chlorine. Yeah, we're essentially multiplying by the subscript that's present in the molecule. Yeah.
Do you want us to write it like this, or can we just solve that in the
It depends on if you're asked for work.
Okay.
Yeah. But this wouldn't be a short answer question. It'd be more complicated than this. The second question was about carbon dioxide, and you had 0.5 moles of carbon dioxide. I'll just do the conversion for oxygen. So if we have 0.5 moles of CO2, well, for every 1 mole of CO2, we have 2 moles of oxygen. So that means in 0.5 moles of CO2, we have 1 mole of oxygen. Any questions on these conversions? All right. Moving on to the next section, which is molar mass. So we'll talk about the molar mass of an atom or molecule, and we can convert between the mass in grams of a substance and moles using its molar mass. So finding the molar mass of a compound is really not too difficult. We look at the atomic mass of each atom that's present in the compound and add up the atomic mass of each element, taking into account the number of each element present in that compound. So it's subscript. So if we're trying to calculate the molar mass of dioxygen, O2, if you look at the periodic table, the atomic mass of oxygen is 16. We have 2 oxygen atoms in that compound, so we do 2 times 16, and that's the molar mass, 32 grams per mole. So the molar mass of O2, 32 grams per mole. Using that process, let's do another iClicker where you are calculating the molar mass of sodium nitrate. So first is writing out the formula. Identify element sodium and nitrate. That is not an element, that's a polyatomic ion. So find the polyatomic ion on your list of polyatomic ions. You have to find the molar mass of each atom from the periodic table, add them together using the subscripts. Another good time to ask some questions as you're working. Or if you want me to just check and see if you have the right process. Like about half, a little over half our calculation in a minute. I'll end it 30 seconds. Five seconds. All right. Okay, not too bad. So if we're calculating the molar mass of sodium nitrate, we need the formula, which is NaNO3. To find the molar mass of NaNO3, we do 1 times the molar mass of sodium plus 1 times the molar mass of nitrogen plus 3 times the molar mass of oxygen, because we have 3 oxygen atoms in that compound. So now we look to the periodic table and plug in each value. So we have 1 times molar mass of of sodium is 22.99 grams per mole. Nitrogen is 14.01 grams per mole. And then oxygen is 16.00 grams per mole. Add all of these together, we get a molar mass of 85. And then when we're calculating molar mass, we use units of grams per mole. We can use that unit for the atomic masses on the periodic table as well, because in 1 mole of oxygen, for example, there's 16 grams of oxygen. So questions on this process? And I'll do another one on the next slide. Okay. So gold medal from the Olympics are not 100% gold. The Olympic gold medal in 2021 is made of silver and is plated with 0.0305 moles of gold. So this question is, how many grams of pure gold are used to make these metals? Here we have a molar amount, 0.0305 moles of gold, which is element Au. And we're looking for grams of gold. So all we need to do here is look to the periodic table, find the atomic mass of the element gold. On the periodic table, 196.97 grams per mole. And then we multiply these together, 6.01 grams of gold are present in the metal. So here we've used the molar mass of a single element. If we have a compound, we find its molar mass by adding up the molar mass of each individual element, which we did on the last slide. So these molar masses for compounds or elements, we have a question, yes?
So like for like the masses, some of them have like 3 decimal points after. Should we just always round to 2?
So this is what I had in my notes. I know that I use a periodic table with 2 decimal places after. If you have 3, you can keep 3 as the atomic mass. That's fine. You'll see both. It kind of depends on the periodic table if there's 3 units past the decimal or 2. So this conversion, if we have the molar mass of a compound or an element, we can use that as a conversion factor. So if we have moles of a substance, we multiply by the molar mass, like this, and here, multiply by grams per mole, and we get mass of a substance. If we have the mass, we say we divide by the molar mass, so we're using a conversion at the top, which is moles per gram, and then that would give us the moles of the substance. Now let's say we start with a number of molecules. We're looking for mass in grams. We always start with the amount that's provided. So we have 5.73 times 10 to the 23rd CCl4 molecules. Shorten the word molecule there. And we want grams of this compound. We know we can use Avogadro's number to convert between molecules and moles. Then we can use molar mass to convert between moles and grams. So we first use Avogadro's number to get to moles. 1 mole is 6.022 times 10 to the 23rd molecules. And now we need to find the molar mass of carbon tetrachloride. To finally convert to grams of carbon tetrachloride. We use a different equation to find the molar mass of carbon tetrachloride. We add the mass of 1 carbon, which is 12.01 grams per mole, to 4 times the molar mass of chlorine, because we have 4 chlorine atoms, 35.45 grams per mole. So I have 153.81 grams per mole as the molar mass of carbon tetrachloride. Now we know how many grams of carbon tetrachloride are present in 1 mole, so we can use that as a conversion in the original equation. Multiply and divide as needed. I get 146 grams of carbon tetrachloride. Questions? Okay. So we've kind of already have done this, but sometimes it's helpful to have all of this written out. So the mass to mole number calculations often involve atoms within a compound as well as the compound itself. So the chemical formula provides the link between moles of a compound and the number of moles of the compound's individual elements. So this molar ratio can be used as a conversion factor. The molar ratio I'm really talking about here is like if we have 1 mole of methane, CH4, we have 4 moles of hydrogen in 1 mole of methane. That's what this whole slide is about. So we've already used that in some examples. So we have this molar ratio, and then the molar ratio can be used as a conversion factor. If we have number of moles of a compound, we can find number of moles of each element, or vice versa. If we know number of moles of each element, we can find number of moles of the compound, continue to find atoms present, molecules present, or mass present. So let's spend a few minutes working on this question. If anyone needs me to go back to a slide, I can do that. But in this question, is this about going back to a slide? Okay, I will after I explain this. So we have, in this question, it's all about ammonium nitrate. So this is a molecule with 2 polyatomic ions. We have the NH4 cation, NO3- anion. This is used as a fertilizer and is one of the top industrial chemicals produced in the United States. So the question here is how many moles of nitrogen atoms are present in a 1 pound bag of ammonium nitrate fertilizer? Another question is how many atoms is this? So number of moles of nitrogen and number of atoms of nitrogen. You start with the measurement given that we have 1.00 pounds of ammonium nitrate. That should be the first part that you write in your equation. That is a measurement of mass, but pounds is not helpful if we're trying to convert to moles, so you do need to convert from pounds to grams, and then you can continue the conversion to moles. So I'll give you all about 4 minutes to start this, and then in the last 3 minutes, I am going to review it. And then what slide do you want to? This one? Oh. Yes. And if you don't know where to start, have some questions, please let me know. I told my earlier class, and I'll do this again today. I want a minimum of 3 questions while you all are working on this. So if you don't hesitate to ask something. Yeah. Okay.
Yeah, literally all your planning is supposed to be Oh, okay.
Well, it's also, yeah, so the end question is only about nitrogen.
Yeah.
Yeah, so I think you have to start here to grab. Dinner migration, and you can get
Like the thing is like it depends.
I'm not paying attention to the time and I see where it's at. So I'll go over this.
Oh, you go to the subway.
That's crazy.
I see it.
Today's my birthday. Oh, come to my room.
You should do another, well, another fraction. You say there's, so the new, like,
Oh, I drink this every day. I live in the car. Oh. So,